All right, so today we're going to talk about comparing two means. You're interested in whether one thing differs from another. So we're going to use what's called a t-test. So before we get into that, we're going to talk about the scientific method just real briefly. So you go out in the world and you make some kind of observation. You're like, wow, it seems like there's more of this here than there is over there. Okay, that's your observation. Then you're going to ask a question. I wonder if it's really true that there's more of this thing here than there is over there. Okay. And you might formulate a hypothesis. You might say, for example, there's more ants in this one place than this other place. And you might think that might be because of the resources or maybe nearer to a water source or who knows, right? So you might come up with some hypotheses for why you might see what you see. And then you'll develop some testable predictions. You say, if I sample from these two different populations and I get a higher abundance of ants in one place than the other, then that might give me some evidence for my hypotheses. Then you go out and you gather the data, you take your samples, you make your measurements, and you run your tests. And that either allows you to reject the hypothesis, your null hypothesis, or it makes you basically, if you can't reject it, then you might refine your hypothesis. And if you do that, if you make a change to your hypothesis after running a test, you're going to set up new testable predictions. And you might be stuck in this kind of feedback loop of the scientific method for a while, coming up with a new experiment, seeing did it work this time, making new predictions, gathering data and testing those predictions, running these statistical tests. And then eventually you're going to come up with some kind of a general theory that helps to push the field forward. Maybe after many, many tests, you've really hit on it and you've said, okay, this is what's affecting ants in this part of the world. And then you might move on to making observations about something else like penguins, right? That's not exactly how it works, but just to try to illustrate the scientific method a little bit better. Okay, so I used some terms that you might not have heard before. The first is hypothesis, and a hypothesis is really an educated guess about something. And it usually involves a why, like why might this be happening? A prediction is similar to a hypothesis, but it's actually an educated guess about the result of a specific experiment. So the hypothesis is a little bit more general, and the prediction is if I set something up like this, then I might have some kind of result. And there were some questions early on, or you might have had questions about this yourself. Do I need to frame my hypotheses in an if-then statement? And I would say, no, the hypothesis is really kind of your guess about what's going on. A prediction would be something that might be framed in an if-then statement. So for example, you might have a hypothesis that eutrophication, which is excess nutrients in the environment, may increase algal growth. That might be your hypothesis. Your prediction might be, if I add nitrogen to this stream, algal growth will increase, right? So you can see it's a little bit more specific and it has an if-then kind of element to it. So in terms of science, we can never prove that our hypothesis is correct. And this is why science has difficulty interacting with politicians and policy and just the general public, because they want us to prove things as scientists. And we really can't prove things 100%. Now, what we can do is we have this tool, statistics, to disprove our null hypothesis. And that's really what we're setting up. We're setting up a method where we can disprove our null hypothesis, which then leads us to accepting our research hypothesis. So in general, the null hypothesis across any kind of test is a hypothesis of no effect. So it's kind of assumed to be true until there's evidence that indicates otherwise. You can think of it kind of like you're innocent until you're proven guilty, right? We also like to think of the null hypothesis as like maybe the simplest explanation, that there's nothing driving the influence or there's nothing driving populations of ants across the world. They're just distributed randomly. So randomness or random chance is often the null hypothesis. And we think of that as the simplest explanation. So maybe you've heard of Occam or Occam's razor. He was a philosopher in the 1200s. Here's just a little statistics joke about Occam's razor. Here's a picture of Occam choosing a razor. Oh, he's saying it's all too complicated, right? Okay, so sorry, I have lots of these little statistics comics, and I hope you either like them or you hate them, but maybe it keeps you awake. All right, so your null hypothesis, back to that. We use the H sub 0 or H naught to kind of denote when we're writing out a null hypothesis. And for a lot of these statistical tests, the null hypothesis is that the pattern we see in nature is due just to chance alone or randomness. If there's a real pattern out there, then the probability that what we see is due to chance alone is probably very small. And so that's kind of the conceptual thinking behind null hypotheses and hypothesis testing. In fact, as ecologists and a lot of other scientists too, we set the probability that it's due to just chance alone at 5%. We're like willing to take a 5% chance that we're wrong. And that is where this P of less than 0.05 comes from. So if the probability that it's due to chance alone is less than 5%, then the pattern we're seeing is probably something real, something true. And that's called a p-value. So for example, here's, let's think about the Western thatching ant, Formica obscuripes. Okay, so here's some pictures of the Western thatching ant. This ant builds large ant mounds for hundreds of thousands of workers. Okay, so here's a picture of an ant mound, and we have these ants in our forests out at Evergreen. So maybe you have a question, you've made an observation, you've seen these ant mounds, and you start wondering, like, are there more ant mounds in fields or in forests? And so this is our example that we're going to use. And the question is, are there more ant mounds in fields or forests? That would be our research question. We might have a hypothesis about that. Okay, so maybe you have one in your head, maybe just hold on to it. And then I want you to consider two statistical populations of interest. The first is all possible ant mounds in forests, and the second is all possible ant mounds in fields. Now, if you could go out there and census them and count them all up, you would just know. You could look at the total in the forest and the total in the fields, and you just know. There's no way we could possibly go out and count up all of the ant mounds in the world. So again, this population level, number of ant mounds per area, the mean is unknowable, okay? And so these population level parameters, like the mean number of ant mounds in forests versus the mean in fields, those are also unknowable. And remember, we use Greek letters to denote population level parameters. So the population means would be mu for the forest versus mu for the field. Now, we can estimate population parameters using what are called sample statistics. And so if we take a random sample in the forest and we compare it to a random sample in the field, we can calculate the sample mean, y bar for the forest versus y bar for the field. And so in this whole statistical lab, you're going to be comparing two means. That's the point of it. Now, y bar is a good estimator of mu, the population mean, when your sample size is large, generally greater than 10, okay? And so your sample should be large, greater than 10, and if you sample randomly, that's going to help you out a lot. So today, we're going to learn how to actually run these statistical tests, how to compare two means, and to answer this question, are there more mounds in fields or forests? So the general form of the null hypothesis is H naught is equal, or H naught colon mu1 is equal to mu2. Okay, so that's comparing any two means. The null hypothesis for the specific example would be H naught. Mu forests are equal to mu fields. So the mean population level mean of ant mounds in forests is equal to the population level mean of ant mounds in the field. Note that your hypotheses are at the population level, even though your testing will be at the sample level using sample statistics, but you're really trying to make some inference about the population. And so this is why it's so important that you design your study so that you're sampling randomly and that your samples are independent of one another. So you're going to go out to several forest plots and several field plots, and you're going to count the total number of ant nests, and say you get this data set here. Okay, so you went to 6 forest plots and 4 field plots, and these are the data you got. Is there a difference? Well, you might be like, oh, I don't know, maybe there looks like there's more in the field, right? But you can't know. You can't just look at data and know. That's why you need statistics. You have to do some things, like you have to maybe you could calculate the sample means. So here we go, sample means. Y bar for the forest is 7, Y bar for the field 10.75. Now is there a difference? Well, you could say, well, there's more in the field, but is it significant? Is it a statistically significant difference? That's the question that statistical analysis will help you answer. So we can't answer the question just looking at the means. Now, we could look at variation around the mean, like the standard deviation or the standard error. And so here's the plots, the means, and the standard error bars. Oh my gosh, look at those error bars. Are they overlapping? Maybe it's pretty close. Like, is there a difference here? We still don't know. This is why you need to run a statistical test. Okay. So we're going to run what's called a resampling test first. And the first thing that we're going to do is we're going to take the difference between the two means. So 7 minus 10.75 is equal to 3.75 nests. Okay, so we get the difference between the sample means, and we find there's 3.75 more nests in the field. Now, what if we mixed all the data up? Would we get a difference value that big? Well, maybe just due to chance alone. Maybe that's something that could happen due to chance alone. So what if we mixed up the data, recalculated the means and the difference, and we did that like 10,000 times? Would that give us a sense of how extreme our difference between forests and fields is compared to the random possibilities in the world? So that's exactly what we're going to do in the next video. We're going to make Excel shuffle these data and do these calculations 10,000 times.